Right, so this is just a teaser for infinite graphs. There's a proper lecture called Infinite Graph Theory, and this is just to sort of get you sufficiently excited to enroll in that course. Here's a teaser for the teaser, just an appetizer about something you can do with infinite graphs that doesn't appear to have anything to do with it. What do we mean when we say that two sets are the same size? Well, normally you would say, well, they have the same number of vertices. So if this has 5 vertices and that has 5 vertices, then they have the same number of vertices, or elements. Now, what does that mean? If you do that properly, then having 5 elements means that something equals 5, namely that. Everything in mathematics is a set. Almost everything is a set. So 5 is a set. And when we say that this is 5, then we'll have the same thing as this line, except instead of that, mod b, we have 5, or mod 5. So it doesn't help to go via numbers. We'll have to define this anyway, if only for the special case that b is the number 5. So let's do it properly, and this is probably what you learned in your first week of mathematics. We'll say that two sets satisfy this if there exists a bijection between them, right? A bijective map between A and B. Now, that definition here satisfies everything that we expect of an equal sign, so that is reflexive, transitive, symmetric, right? Just composition of maps shows that if there's a bijection from here to there and from there to there, then there's a bijection from there to there and so on. So, as you may have noticed, I stopped short of saying this is an equivalence relation because it's not a relation on something like the set of all sets or something, because we don't have the set of all sets. But never mind, it satisfies everything that we expect of an equivalence relation. It's reflexive, transitive, and symmetric as far as those are defined. So that's fine. How about this then? That A has at most as many elements as B does. There we use the same definition. So we say there exists an injection, an injective function, an into function from A to B. And that again satisfies everything we expect of an order relation. For a start, it's well defined. So if you replace A with an A prime that satisfies that with A, then if there's an injection from A to B, there's also one from A prime to B, because we're just preceded by this bijection. And similarly, if you have a B prime on the other side. So it's well defined on these equivalence classes, if indeed that's what they were. And it's also clearly reflexive. So there's an injection from A to A, and it's transitive if there's an injective map from A to B, and from B to C, then there's one from A to C. So the one thing that's not quite so clear is antisymmetry. So, and this is traditionally called a theorem. Let me write these names in alphabetical order. Bernstein, Cantor, and Schröder. And the theorem says that if we have this both ways, then we have that. That's what you'd expect of antisymmetry. It's not a relation on a set, so never mind, but if there's an injection from A to B, and if there's also an injection from B to A, then we want that there's a bijection from A to B. And here's the funny little proof. When you do this in your, I don't know, beginner's course in mathematics, or maybe even in a set theory course, it takes sort of half a page, usually, and here's a one-liner which will fill the rest of the board. So let's write down what this means, and then deduce that. What is A is at most cardinal A, is at most cardinal B? Well, it means that there's an injective map from A to B. And so green is the map from A to B. For every little a in big A, we find a partner. And likewise, there's an injective map from B to A. So for every little b, we find we can map that to some A. In an injective way. And we ask, is there a bijection between A and B? Okay. And there's a simple little trick, and that is just to look at the graph defined on the vertex set A union B by these colored edges. And we observe that this graph has vertex degrees at most 2. So every vertex on the left in A sends a green edge to the right by courtesy of this green injective function. And every vertex on the left sends an edge to the on the right sends an edge to the left. And sometimes a vertex on the left is also the recipient of a blue edge, but not always. And likewise on the right. So the vertex degrees are 1 or 2. And now just close your eyes and look at the components of this graph. Components of any graph with vertex degrees 1 and 2. So what could they be? Well, if we start at a vertex here, from every vertex in A, we have a green edge to the right. And then from every vertex on the right, we'll have a blue edge to the left. And then we can go back to the right, and so on. And this can never stop. And if this first starting vertex wasn't a recipient of a blue edge, then this is the entire component that contains that vertex. We can't have another incident edge here because it can be neither red nor neither blue nor green. So that'll be a component. But then this might have been the recipient of a vertex of a blue edge. So we would also have two-way infinite paths as components, possibly. I mean, this, yeah, But if we always ask, are you the recipient of a suitably colored edge, then the vertex might always say no, because we're going the wrong way. We're going against the direction of the maps. So if it does say no, we're in this case. And if it never says no, if none of these vertices ever says no, then we're two-way infinite. And then, of course, you can have finite components. And these will have to be, they can't have vertices of degree 2. Well, okay, let's get to that in a moment. We can have even cycles. Every vertex has degree 2. We saw already that we can't have finite paths because we never stop. This never stops. So, yeah, we can have infinite paths. That can be either one-way or two-way. And we can have finite cycles. And if we have a finite cycle, obviously, it has to be an even cycle. Okay, so these are the possible components. And what do we want in order to have a bijection? We want a one factor of this graph. We want a matching of all the entire vertex set. And that's easy, unless you're a set theorist, but we're not set theorists, so it's easy. Here, in this component, you clearly have to use the first edge because that isn't incident with any other edge. So we use this green edge. And then we have to use every green edge in that component. Here, we can use either all the green edges or all the blue edges. We have to do one or the other to give every vertex degree 1 in our set of selected edges. And here, we can also take either all the green or all the blue edges. So what we do here, the selection of the green or the blue edges here involves a choice. Here, it doesn't involve a choice. It's clear what we have to do. Right, and when I say involves a choice, then this is what the set theorists among you will notice is possibly, potentially problematic, but not for us. So, done. Right, that's the neat little proof of the Cantor-Schröder-Bernstein theorem. Essentially, that this is a partial ordering. Okay, questions? Right. Then that was the appetizer. Now an interim course of some tidbits that are just exciting and nice to see. Things in infinite graphs that don't happen in finite graphs. And let me just make a list of, not a very long list, of some funny properties that infinite graphs can have. One has nothing to do with graphs, it's just, let me write it like this. Infinite minus finite is still infinite. So if you take an infinite set and you delete a finite subset, what remains is an infinite set. If you're serious about mathematics, that needs proof. We're not serious now, so we're serious about graphs, but not about the rest. So we declare that as obvious. But here's a nice example. If the connectivity of a graph is infinite, that's the smallest. There's an appendix on cardinal numbers in the book that lists everything that you need to know about sets, really, including cardinals, to do infinite graphs, and it's just a couple of pages. It's not more. So I'll assume now that you know what L(0) is. It's the smallest infinite cardinal. And if the connectivity of a graph is infinite, then it has an infinite complete subgraph subdivided in it somewhere. Okay, here's how not to prove it. Pick the vertices. Here's our G, right? Now we pick infinitely many vertices. And then we say, yeah, we can easily link them up using that. Answer, no, we can't. Why not? Because it might happen that we can't link this vertex to that because all its neighbors are the other infinitely many vertices that we have already picked as branch vertices of our TK(L)(0). So the moment we pick infinitely many vertices, we can spoil whatever we have as an asset, even if the asset is infinite. But if we only do something finite, we're unlikely to spoil that. So let's do it like that. And construct this in one infinite sequence of steps so that after every step, what we have done is finite. So we start with a vertex, then add another vertex, and join that by a path. And then this is a branch vertex by decree. That's our next branch vertex by decree. Now we add a new branch vertex, and we want to join it to this, and we can easily avoid this path, so we join it to that. Then we can easily avoid this, and join it to that as well. And when we have done that finitely often, we can happily pick a new vertex outside and join it to the finitely many branch vertices that went before it, avoiding all the stuff that connects those, right? Using that. And after, I would like to say omega many steps, so that's after, when every natural number has occurred as a step, then we have this. Right? We will have picked infinitely many branch vertices. So at the limit, L(0) or omega, suddenly these TKNs unite to become a TK(L)(0). But it only happens then. Okay, is that clear? Good. Second, can we make this TK(L)(0) spanning? Can we use every vertex? Notice that this doesn't happen automatically. We can do this infinitely often, and still there might be infinitely many vertices there that we never touched. Can we ensure that we do use them? Yes, easy. Another standard technique, we enumerate the entire vertex set first. So we're assuming that G is countably infinite. Enumerate the entire vertex set, and then when we come to pick a new branch vertex, which happens infinitely often, don't pick just any new vertex, but pick the vertex with the smallest index that we haven't used in our overall enumeration. So all these get picked eventually. Right? Not every one of them gets picked, because some of them will appear on these linking paths, right? But we will be using up every vertex of G. Okay. So next, fun little property. When you take a countable union of countable sets, then what you get is still countable. The standard way of using that is that you want the union to be small. And what you have is that the ingredients are small, and you take only a few, namely countably many of them, and then you say, okay, then the union is still small. But there's a fun little way to apply that the other way round, and I want to show you an example of that. So you can artificially write any countable set, for example, the set of natural numbers, as an infinite union of other infinite sets. Right? Just because because of this equality here. And let me give you an example of that. So what I want to prove is that if the edge connectivity of G is infinite, then G has infinitely many edge disjoint spanning trees. Right, G is again a countable graph. Right. Now, earlier we had connectivity infinite, now we have edge connectivity infinite, slightly weaker. And we want infinitely many edge disjoint spanning trees. So once more, here's our G. Here's not to prove it. Here's how not to prove it. Take the first spanning tree, then try to add the second spanning tree, and so on, always hoping that this will enable you to choose edges so as to complete an entirely new tree on the remaining edges, those that you haven't picked yet, that contains every vertex of G. And the reason that fails is the same thing, the same reason as what made that fail earlier. When you have picked infinitely many edges already, it might be, for example, that you have picked all the incident edges with this particular one vertex and you put them in the first tree. Pretty stupid to do that, but I mean, I'm only trying to prove that you have to be a little cleverer than that. Okay, so this is not how to do it. How then does one do it? Well, same idea as before, plus the ingredient of 2. So, divide the natural numbers into infinitely many disjoint infinite sets Ni. Then go through n in your steps, and if the n that you're looking at lies in an I for some particular I. Every little n will lie in some ni. Look at the next little n in the construction. That will lie in some ni. And then try to do something for the ith spanning tree. I have to tell you what to do for it, but that's pretty clear. After any finite number of steps, we have added finitely many edges to some of the trees. The trees are going to be indexed by these I here. Whenever we look at n, whenever an n lies in ni, we're doing something for ti. And what do we do for it? Well, we pick a new vertex, and we use this to join it to ti, to whatever we have done, we have constructed of ti already. If we haven't started ti, start it here. And similarly, in order to make sure that we really catch every vertex in every ti, we start with a fixed enumeration of all the vertices, and when our step n tells us to do something for ti, we pick the smallest vertex not yet in ti in this overall enumeration. And then we link that vertex to whatever we have constructed of ti already, which is always finite. And all we've done is finite. We have started only finitely many t's, and each one of them with only finitely many vertices and edges. So we can always use that in order to join any vertex we like, and I just told you which one we like, to whatever we like down there. Yeah? And that's it. And after exhausting all the little n's, suddenly all these there are infinitely many trees, not only started but complete. It all happens at once at the limit step. Is that clear? And the trick is to sort of consider each of these ti infinitely often by partitioning n into infinitely many infinite sets. Questions? Can we even make sure that we use the entire set of edges as well? We're using in every ti all the vertices. That's because they're spanning trees. Can we use up all the edges of G? Okay, I'll leave that as homework to think about. It's a similar argument as enumerate all the vertices, make sure that you attach the lowest next one to the tree that you're looking at, and you have to do something similar for edges. Okay. Next. Maybe I'll phrase this as a question. Can we have a set of uncountably many sets that meet pairwise finitely but have only countable union. Right? So we want uncountably many subset of some countable set, many subsets. That meet only finitely pairwise. We want uncountably many of them. Right, so most of these sets will have to be infinite, these subsets, right, because there are only countably many finite subsets of a finite set, of a countable set. Right, but we want uncountably many subsets. So most of them are going to be infinite, but we want them to pairwise meet only finitely. And if you think about it like this, you get sort of chaotic, at least in my head it does, unless you've seen the following picture. The following picture is really, really easy, very simple. That's the binary tree. And what are the sets that I'm talking about? Well, the sets are going to be the one-way infinite paths, or the vertex sets of the one-way infinite paths from the root up. Right? Any two of them, you can think of them as 0-1 sequences. Any two of them, if they're different, they'll have to part ways somewhere, and then they'll never meet again. So if they're different, their intersection is indeed going to be finite. How many are there? Continuum many. So very much uncountably many. Yeah, and I mean, it's completely obvious here. It's pretty mind-boggling there. That's why infinite graphs are useful. Not only that. Okay. Okay, okay, let me write wonders happen at infinity, at limit steps, at limits. And the example I want to give you, so these correspond to 1, 2, 3. Now, the example I want to give you here is for every k and g, natural numbers, there exists a graph with connectivity at least k and girth at least g. All right, so that's true even for finite graphs and pretty hard. That was the R.Diestel theorem that I told you about in the chromatic chapter. Right, there's a graph of chromatic number and girth as large as we like simultaneously. And if you make the chromatic number just a little bigger, like, I don't know, 4k plus 1 or whatever, then you'll find in that highly chromatic graph, critically, that chromatic graph, which has min degree, that chromatic number minus 1, and that has a subgraph that's highly connected, like a quarter of that. So you get it for finite graphs, but it's pretty hard. For infinite graphs, it's totally easy. And yeah, so maybe this space will do. How do we construct such a graph if we're allowed to make it infinite? Easy. We start with a long cycle. So bigger than G. Okay, that's a good start for G. It's not such a good start for K, because it's not K connected, but never mind. For any pair, add paths say at least K paths to join them, new paths, and make them long so that you don't create a short cycle. And do that for every pair. Okay? Well, you've added lots of vertices now. So there are many more pairs. We'll have to do that again, and so on. Yeah, but at any step, we've only done finitely many. So you can take all the pairs of the cycle and add paths for those, just to keep things sorted in your head. Then take a deep breath, look at what you have. You have finitely many vertices. For every pair, add many long paths between them. Close your eyes, take a deep breath. See what you have, finitely many vertices for every pair, and so on. Right? Do that infinitely often, and there you are. Okay. Can we get infinite connectivity? We can't get infinite girth. It doesn't exist. But can we get, I mean, it will be a tree. And a tree is not going to be highly connected. But can we get infinite connectivity? Yeah, not a problem. For every pair, first time round, add one path. After your first nap, when you look again, for every pair, add two paths. After your second nap, when you look again, for every pair, add three paths, including vertices that you've treated before. So pairs of vertices on the original cycle get looked at infinitely often too. Right? So for every pair, you get back to that pair infinitely often. And first, you'll be adding one path, and then two different paths, and then three different paths, and then four different paths, and so on. And since the new paths are always disjoint from everything you had before, these are, in fact, disjoint sets of paths. Okay. That was the fun bit. We'll get a little more serious now, but any questions? Okay. Right, so let's do Menger for infinite graphs. In a finite graph, it says the non-trivial direction of Menger says if you have a graph G and you have vertex sets A and B and G don't have to be disjoint, and K is the smallest number of vertices that will separate A from B in G. I think that's what I want K to be. Yeah. Then there are K disjoint AB paths. Right, that's the finite Menger theorem that we know. Proof for G infinite, K finite. Well, K finite. We have A and we have B. Let's take as many AB paths, disjoint AB paths as we can find. I'm saying as many as we can find. I'm not saying take any maximal collection of disjoint AB paths. Take as many as we can find. One such set that is as large as possible. And suppose that's not big enough. So suppose it's smaller than K. Let's call this cardinality L. Then let's look at vertex sets, call them X, that pick one vertex from each of these paths. For every such collection, there will exist a path from A to B that avoids X, because this set has only L fewer than K vertices, and K is the least number of vertices that you need to separate A from B. So deleting the blue vertices here will not separate A from B. So there's a path that avoids it. Do that for every such set X. And then consider the graph that consists of all the paths in P, union the appropriate PXs. So for every little colored X, only finite many, we choose such an avoiding path PX. That's a finite graph. So apply finite Menger to A and B in this particular graph. So L is not big enough for there to be L vertices separating A from B in H, because any vertex set of at most L vertices, in order to separate A from B in H, will certainly have to pick a path from every, a vertex from every path in curly P, if it is to separate A from B in H, because all these paths are in H. But then we've used up our L vertices, and the P that corresponds to that choice is also in H, and we haven't picked a vertex from that. So there is no AB separator of size at most L in H. So there are more than L AB paths in H by Menger. Maybe not K, but certainly more than L. But then these more than L AB paths exist also in G, because H is a subgraph of G. And that contradicts our choice of curly P, which was a set of disjoint AB paths as large as possible. We just found a larger one. I mean, we haven't found it, but Menger tells us, finite Menger tells us that it exists. Yeah, okay. So that was easy. Proof for infinite K. Right, so look at the appendix on sets for a precise explanation of what that means. K is the least cardinality of a set of vertices separating A from B and G. Now, things become even simpler. We just take a maximal set of disjoint AB paths. Nothing about numbers now, nothing about cardinalities, just a maximal set of disjoint AB paths. Right. Now, how many paths are there in P? Certainly infinitely many. If there were only finitely many, each of these paths is finite, then the union of all these paths will be finite, but this union separates A from B. Why? If it didn't, there would be another AB path outside this union, so P wouldn't have been maximal in this very weak sense. Okay, so P has got to be infinite. But if it's infinite, then its cardinality is no bigger than itself. Right? The union of infinitely many finite sets is still infinite of the same cardinality only. So a countable union of finite sets is still only countable. Right. That's also in the appendix, needs proof. In fact, much more is true. So if all these, well, it doesn't matter. Right, so then we have found a set P of cardinality exactly K as we wanted it. Right? So if P had fewer than K elements, then its union would also be smaller than, would have this smaller cardinality, still infinite. but then we'd have a separator of that smaller cardinality. And we don't, by definition of K. So that was completely trivial. So is Menger's theorem trivial for infinite graphs? Well, fortunately not. There's the Erdős conjecture, made, I think, like 1960 sometime. And it's just a structural version of Menger, one that avoids speaking of cardinalities. And it says, for every G and vertex sets A and B, there exist two things. A set curly P of disjoint AB paths and also an AB separator on P. And on P means that it consists of exactly one vertex from every path in P. A consequence of P and X having the same cardinality when this is finite. But now we're not talking about cardinalities. We have this silly equality here, which prevents us from deducing that a set X of no more vertices than we have paths in curly P must have this form. It no longer does, because it might consist of all the vertices on the paths in P. So we just require this explicitly. So the assertion is for every G, for every set of for every two vertex sets A and B, there are two things exist at the same time: a set curly P of disjoint AB paths and a separator of precisely this form, picking one vertex from each path. Yeah. And this was eventually proved after many decades by Aharoni and Berger. I think the proof appeared in 2009. It's not quite as correct as we might hope it is, but it is correctable. Unfortunately, it's like with these claimed things. There's not so much merit in writing down a correct proof when there exists a proof, and everybody who's read the correction will say, oh yeah, but that's the original proof just patched up. However, when you read the original proof, it's not a triviality to patch it up, but it is possible. So my understanding is that this is indeed a theorem now, and it's the Aharoni-Berger theorem. Okay. Questions? Good. Then let's start something else. Yeah, it comes by the name of, it sounds a little terrifying, but it isn't. So compactness proofs, compactness arguments. Yeah, it does have something to do with compactness, but you don't see it in the way I'm going to present it now. Let's look at a graph G, and let's assume that for every finite subgraph of G, the chromatic number of that subgraph is at most k. K is some finite number. Right, so here's G. Every little h has chromatic number at most k, so we can k color it. Right. Question, can we k color the entire graph G? Okay, let's make a start. Pick a finite subgraph. Use what we have, that we can k color it. So we k color this. Now we want another vertex to incorporate another vertex, and it has some neighbors in there. If we're unlucky, these use up all the k colors that we have. We don't know when we just look at H without looking at the rest. And there may be many vertices outside, so the graph is not what we call locally finite, that every vertex is finite degree. It's just any, say, countable graph. Okay, so maybe we can't extend this coloring to even incorporate one more vertex. But we can say, oh, well, let's not give up so quickly. We can still color that graph with k colors. So maybe we have to make some adjustments here. Yeah, but then same happens next time. Okay, we can still make a k coloring of that. So does that sort of converge? Does it give a k coloring at the end of that process when we've considered every alpha vertex? Well, it depends on whether the color of this vertex, say, settles down, or whether we change it infinitely often. If we keep toggling it, then when we're done after all these steps, there's no well-defined color of that vertex. If we stop changing it, we can use that as the well-defined color. So the question is really, well, can we make sure that we don't toggle infinitely often at any vertex? And that's not so clear. And now, you may have guessed it. König's infinity lemma. König's infinity lemma, or simply König's lemma, says that if we have a sequence of finite sets Vn, and define a graph on the union of all these disjoint sets, disjoint finite sets, in such a way that every vertex in Vn, for every n, has a neighbor in Vn minus 1. But not necessarily the other way around. So a vertex in Vn need not have a neighbor in Vn plus 1. Then there exists an infinite path through this graph. That starts at V1, V0. Right, so how do you prove that? It's easy to get finite paths as long as we like. We just have to start late and can find our way back. So we can start at n as large as we like and find a path of length n back. But how do we find an infinite path? And the way to do that is to, well, use what we have. We look at all these paths that come back from the late Vn's. There are infinitely many vertices here, infinitely many n's even. So there will exist one of these finitely many vertices at V1 at which infinitely many of those end. Pick that vertex. So infinitely many of these finite paths that come from later and later Vn's, infinitely many of those end here. Well, then infinitely many of those must have the same last edge, because there are only finitely many edges out of this vertex. Right, so there exists a vertex in V2 that lies on infinitely many of those paths. Not the same infinitely many, a subset, but an infinite subset. And that has an infinite subset of paths that all use this, and that has an infinite subset of paths that all use that, and so on. So we can sort of move forward, and after every finite number of steps, we can still move forward because we have sort of decimated our infinite supply of paths by taking an infinite subset, an infinite subset, an infinite subset, and they get really, really small, these infinite subsets. But they're still infinite after any finite number of steps. When we're done, they're all gone. But it doesn't matter. We have our yellow path. Okay, so that's the proof of the infinity lemma. How do we prove that G can be colored with K colors? Well, we take as Vn the set of all K colorings of Gn, and Gn is what the first n vertices induce in G. So I said we're in a countable graph G. Let's enumerate all the vertices. And then whatever the first n vertices induce, let's give that a name, call it Gn. That's a finite graph. Many, many finite graphs do not have this form, right? But all these graphs do have, are finite, and therefore they have a coloring with at most K colors. Maybe Gn has many colorings with at most K colors, but only finitely many, because it's only got finitely many vertices, there are only finitely many colors to dish out to these vertices, so there's only finitely many ways of doing that. Right? So the set of all K colorings of Gn is finite for every n. Call that set Vn. Okay. So we're set up for the vertex set here. How do we define edges? Well, this vertex here, what's that? That is one particular K coloring of Vn, of Gn. If you delete the last vertex, you get Gn minus 1. And if you delete the last vertex in this k-colored graph, you get a k-colored Gn minus 1. It's one of those. So draw an edge from here to that one. Notice that we don't necessarily have edges from a vertex to the right. We don't necessarily have to be able to extend a given coloring by even one vertex or this next vertex that Vn plus 1. But we can always go back. So we have exactly what the infinity lemma asks. So there exists this infinite path. Okay, how do we get from this infinite path to a k-coloring of all of G? Okay, I have to do two things now. I have to give you the definition of the coloring. I have to tell you, given a vertex, what is its color? What is its color? And then I have to show you that this is a proper coloring, that adjacent vertices get different colors. Okay, what's the definition? You come and give me a vertex that you want me to color. I'll say, okay. You give me a little v, and I look, when is the first time little v appears in Vn? So I look for the smallest n such that v is among v1 to Vn. Right? Well, that's going to be Vn. Never mind. So look at some Vn where this v is colored. And I say, well, give it that color. In fact, I could be really bold and say, take any Vn where your little v appears and give it that color of the yellow coloring in that Vn. And then you can ask, well, is that well defined? Because my little v is in many Vn's. Yeah, but the later colorings induce the earlier ones. So it is well defined. Okay, so we have a well-defined map from the vertex set of all of G to k colors. Is it a proper coloring? Yes, of course it is. Take two adjacent vertices. One of them appears at some point, and the other will appear at some later point. And at that later point, both vertices have the yellow coloring from that Vn. And in that coloring, since they're adjacent, they get different colors. But the earlier point has the same coloring as it does here, where we chose it. So it's a good coloring. Yeah. So basically, compactness for our countable graphs, certainly for locally finite countable graphs, is pretty much the science of applying the infinity lemma, no more. Right, so that can be phrased in terms of Tikhonov's theorem about compactness of product spaces. The product of compact spaces is compact, and you can read up on that in the appendix on infinite sets. Right, there are sort of like 4 or 5 different ways of phrasing that. Some of them are slightly stronger than others, but for countable graphs or even locally finite graphs, they all mean the same thing, and they are equivalent to König's theorem, König's lemma for those graphs. Yeah, so we have time for another application. Unfriendly partitions. That's a famous problem in infinite graph theory. It's an unsolved problem, the general problem is, but I'll show you a simple case that once more uses the infinity lemma in the proof. So what does it mean? A partition of the vertex set of a graph is called unfriendly if a vertex has at least as many neighbors in the opposite class as in its own class. I'll tell you why it's called unfriendly. I will call it friendly, but so whoever invented this has a notion of friendly that is something like coziness in your own peer group, rather than being nice to others. So anyway, so once more, a partition of the vertex set into two classes is unfriendly if every vertex has at least as many neighbors opposite as in its own class. But we're looking for unfriendly partitions, so they're nice. Maybe they're friendly after all, but, right? So does every graph have such a partition where every vertex has at least as many neighbors in the opposite class as in its own class? Well, look at a vertex here that has fewer neighbors in the opposite class than in its own class. Just move it across. Right, and now it has those more neighbors here in what will be the other class than those neighbors in what used to be the other class and is now its own class. Done? We can do that with every vertex, can't we? So one by one. Yeah. So let me phrase it positively. In order for this to work as a proof, we have to make sure that this process stops. This graph can be finite or infinite or whatever. How can we ensure that this process stops? Rather than giving you an example where it doesn't stop, which would be another way of treating this, but how can we ensure that it's more positive? How can we ensure that it stops? Well, if we can find some parameter that is monotone, that keeps, say, going up with every such move, then if we can prove that it can't go up more than, I don't know, so-and-so many times, then we can say, well, when we have completed so-and-so many times moves, it will have stopped. And if it stops just by itself, then every vertex is happy. I call vertices happy if they have more neighbors, at least as many neighbors in the opposite class as in their own. So can you think of a parameter that does go up? If the graph is finite, the number of cross edges will go up with such a move. Right? Not if the graph is infinite. Right? If you have infinitely many cross edges and then you move one across, then you sort of increase infinity by one, which is still the same. So for finite, this proves that every finite graph has an unfriendly partition. So let's prove that every locally finite graph has an unfriendly partition. I don't know which number this is. So proposition, every locally finite, let's say connected to make it countable, graph has an unfriendly partition. And we're in the same situation as here. So for every finite subgraph, we know there is such a partition. Yeah, but it's not clear that we can always extend the partition that we have found to a bigger finite subgraph. And so the idea would be, the first proof idea to use König's lemma would be to define Vn as the set of all unfriendly partitions of Gn. Okay, that's only finitely many possible partitions. Gn is a finite graph. They exist, so these are, I should have said earlier that these sets are non-empty. Right? Have to be non-empty. So there is a finite, there is an unfriendly partition of Gn for every n, and how would we define the predecessor here, the edge back? Well, in the obvious way, we have a partition of Gn that induces a partition of Gn minus 1. Trouble is, it needn't be unfriendly if that was. Why not? Because this Vn that we deleted might be needed as an opposite neighbor here, and it's no longer available. So some vertex, this vertex here, might have this Vn over there, so this partition here would be good, unfriendly, perhaps as a partition of Gn, but when we delete Vn, the induced partition of Gn minus 1 is no longer unfriendly. So we have a problem. And here's a nice way out. We take the partitions of Gn in which those vertices are happy, such that every V whose G neighbors are all in Gn is happy. Has at least as many neighbors opposite as in its own class, right? So we're just weakening the requirement of unfriendliness by, we're still considering partitions of Gn, but we're not asking that every vertex shall be happy in the sense of having at least as many opposite neighbors as in its own class, but only some vertices have to be happy. Those, all whose neighbors happen to be already in that Gn. And we don't care if other vertices are unhappy. Okay, but now this works, right? So I said earlier, a partition of Gn might, it will induce a partition of Gn minus 1, but it need not, if it's unfriendly, induce an unfriendly partition here because the vertex we deleted might be missing as an opposite neighbor. But now, under the new definition, this vertex here would not be contained in Gn minus 1, so it will be a missing neighbor for some little v in Gn minus 1, but that little v doesn't have to be made happy under this definition. So we don't care about how many neighbors that little v has in Gn minus 1, left or right. Okay, so that defines this these edges here. When you write it down, you will notice that to define this properly, you have to give these classes names. So we assign to every, a partition of Gn is an assignment of the names left and right to every vertex. And then you can say, yeah, that induces a partition here. Every vertex inherits a label left or right. But you have to sort of come down and make this specific in order to define this inducing properly. That's a little technical aside. And then this yellow path will define a partition of G, of the entire G. How? Well, for every little vertex, I look, where does it appear? And it carries a little label, left or right. And I'll put it left or right. And it doesn't matter where I look, because the later assignments of left and right will induce the earlier assignments because they're all on the yellow path. Okay, so we have defined a partition of the entire vertex set of G into left and right. And unlike these, that's going to be an unfriendly partition, because since the graph is locally finite, every vertex has only finite degree. So for every little vertex, for n big enough, that vertex will have all its neighbors in this Gn. So in the yellow partition of that Vn, this vertex is already happy. And since we chose the left or right of that partition to place our vertex in the partition of G, and all these other neighbors are also have their left and right assigned to them in G, as they do in this partition of Gn because it's yellow, the assignment of left and right to the neighbors will also be the same as what we gave those neighbors in G. So every vertex will indeed be happy in this entire partition of G, although it's sort of cobbled together of lots of inferior partitions that are, none of which is good, but the limit of all those is good. Yeah, so that's sort of similar to saying the color here toggles only finitely often, and then it stabilizes. The neighborhood of a vertex stabilizes, and from where it stabilizes, this vertex has to be made happy. Yeah, so questions?